All right, so we want to think of these two mapping diagrams as one is the function, one is the inverse of that function. So if you look at the function one, it's the one that just has f. Remember that the domain would be in one bubble, right? Your x values in one bubble, and then your range or your outputs would be in the other bubble, right? We consider this your f of x, right? So you had one input, which is a would go to 3. You would have an input b, that would go to 1. You'd have an input c, that would go to 2, right? That's your function, that's how it behaved. And we know it's a function because every input goes to a unique output, right? A only goes to 3, B only goes to 1, C only goes to 2, right? We don't have one input that goes to 2 different outputs. So we know we're working with a function in terms of the literal definition of a function. What does inverse function do? Well, the inverse function basically reverses the mapping. It moves the outputs into the input and the inputs into the output, right? But the connection is still the same, right? So if you think about what happens with A, well, A goes to 3, but in the inverse, you actually have 3 as the input, but it still only connects to A, right? So it's basically a reverse of the original function, right? The outputs become the inputs become the outputs, but the connection between the input and the output remain the same. So A goes to 3, the inverse function sends 3 back to A, right? A to 3, 3 back to A, right? That's essentially what the inverse function is doing, okay? We can also track that with B. B is the input, B goes to 1. The inverse function will take 1 as the input, send it back to B, right? And then the lastly with C. C goes to 2 in the original function. In the inverse function, 2 goes back to C, right? So the connections that have been forged remain the same, they just get reversed. All right, and that's essentially what an inverse function does. Okay, so it undoes or reverses what the original function did. Okay. Now, any questions about that? Right, so that's kind of the concept, that's the idea. Our focus today will be how do we find the inverse of a function algebraically. So it's going to be a lot of algebra, a lot of moving variables around, things like that. Okay, let's talk about the notation. All right, notation is key here because a lot of times it can be misunderstood. The notation of an inverse function is written as f inverse or f to the -1 power. Okay, that's how the inverse function is notated. It's f to the -1 power. But what it stands for is simply the inverse function. Okay. Now, what does this diagram represent? This is a commonly kind of misconstrued concept that inverse means reciprocal, right? Reciprocal where you just flip it and you send the numerator into the denominator and the denominator into the numerator. That's not what it is, right? It's not that simple. I wish it was, but it's not. So when you see the notation for f to the -1 power of x, it means the inverse function, right? Inverse does not mean reciprocal, right? This is reciprocal, flipping 1 over f of x. That's reciprocal. Let me highlight it, right? So this would be a reciprocal, but it is not the same, right? That's why it's not equal to the f to the -1 power of x, okay? So as a notation here on the side, inverse is not the same as reciprocal. Okay, so if you have a question that says find f inverse of, or f to the -1 power of x, that means they're asking for the inverse. You got to take the inverse. Do not just simply flip the function around because that would be incorrect. Okay. So that's just something to keep in mind. All right. Now we finally get to how do we find the inverse, right? There's 4 steps. Pretty easy to follow. Okay. So we're going to try out the steps with an example, and I think it'll make more sense. All right, so we're going to start here with example 1, where they want us to find the inverse of f of x, right? So we have f of x, we want to find the inverse, right? So it's not just flip the function, right? We're going to go through these 4 steps to find that inverse, okay? So let's start with step 1. The first step says to rewrite f of x as y, right? We know that, right? F of x does mean y, so we're going to start with that. So y is equal to 3x plus 15 all over 7. Okay. By the way, this first function that we're working with, this is a linear function. It might not seem like it. Okay, but it is, right? That 7 is just the denominator. So you could really think about this being 3 over 7x plus 15 over 7, right? That's nothing fancy. That's just a linear function. Mx plus b. Okay. All right. Step 2 is to exchange x and y, right? So you're going to swap x and y. So instead of y equals 3x plus 15 over 7, this becomes x equals 3y plus 15 all over 7. Right? So we swapped it. Yeah, there you go. Okay. So far we have step 1, rewrite f of x into y. Step 2, swap the x and the y. Now we have step 3, which means solve for x, aka get, not solve for y, I'm sorry, solve for y. So get y by itself. Okay, that's what we want to do. We want to get y by itself, right? That's what it means to solve for y. So with step 3, okay, what could I do to begin that process? If I wanted to get y by itself, what could I do? We could split it, but that actually might make it a little bit more difficult. Yeah, we want to multiply both sides by 7 because that helps us get rid of the denominator of 7, right? Yeah, so we'll multiply both sides by 7. So we arrive at 7x is equal to, here, because we multiplied the whole fraction by 7, that cancels the 7s out, right? So we end up with just 3y plus 15. Okay. I'll continue the work up here. So we're still trying to isolate y. What do we do next? Yeah, subtract 15, right? Subtract 15. We end up with 7x minus 15 is equal to 3y. And then finally, how do we get y by itself? Yeah, we'll divide by 3, right? So divide both sides by 3. Let me make this more clear. Okay, so we end up with y is equal to 7x minus 15 all over 3. Okay, and then finally, step 4 tells us to change y into f inverse of x, right? So we're going to go to y, we're going to change that into the notation f inverse of x. Okay, so now step 4, 7x minus 15 all over 3 is equal to f inverse of x. And then that would be my inverse function. Okay, that's my inverse function. Any questions about how to find the inverse of a linear function for that first example. Okay, let's move on. All right, so now next example, we're looking to find the inverse of g of x. What we have this time is a rational function. Okay, so it's the same steps, right? You still follow step 1, 2, 3, and 4. It's just that you have a different function. So you have to treat it slightly differently in terms of the solving component, but in terms of rewrite, exchange, solve for y, change y into f inverse, those are the same steps. Okay, so let's begin here with this one, right? So first rewrite f of x as y. This time we don't have f of x, we have g of x. Same idea though. We're gonna go ahead and, let me get my colors here. We're gonna start with step 1, which is to change g of x into y. So we have y is equal to -3 all over x plus 1. This is all crooked, let me fix it. Okay, plus 2. Okay, so this time notice this is a rational function, not a linear function, because where is the variable? It's in the denominator, right? So when it's in the denominator, when x is in the denominator, that's how you know this is a rational function, okay? All right, step 2 was to, or is to exchange x and y, right? We need to exchange x and y. So we're gonna rewrite this as x is equal to -3 all over y plus 1 plus 2. All right. Here comes the fun part. We need to solve for which variable? Which variable do we need to isolate? Yeah, we need to solve for y, right? So we need to find a way to get y out of that denominator so that we can set everything else equal to y. So with step 3 here, where do you think we would begin? If our goal is to get y by itself. Yeah, let's start there, right? Let's move the constant over. So we would subtract 2 on both sides. The terms eliminate on the right side. We end up with x minus 2 is equal to -3 all over y plus 1. Okay. Let me guide you through the next few steps here. All right, here's what we're going to do. First, I'm going to wrap the denominator in parentheses. I'm going to wrap the term x minus 2 in parentheses. Right. I'm also going to establish a denominator of 1 underneath the term x minus 2. All right. I'm doing all of this in preparation because I'm going to do a cross multiply. Okay. I'm going to do a cross multiply because that's going to help me get the term y plus 1 out of the denominator. Right. So the whole term y plus 1 is going to get moved out when we do this cross product. Okay. So the cross product will involve x minus 2, the term, times y plus 1, the term, equal to the other cross product, which will be the -3 times 1. Okay. So what we'll end up with here, bring it up to the top, is going to be the product of x minus 2 times y plus 1 equal to the product of 1 times -3, which is still -3. Okay. Do you guys follow what I've done so far? Okay, so it was just a cross product, right? We first moved the constant, and then we had a term x minus 2. We had a term y plus 1, right? Easier to see those terms when they are wrapped in parentheses. Okay, so that's why I went and did that extra step. Also, because when I multiply them on the cross product, I can keep them separate within their own parentheses, right? So that's why I have x minus 2 contained and then y plus 1 contained. All right. Your next step might be to distribute, but if you distribute, you'll actually make the problem a lot more complicated than what it has to be. Remember what the goal is. The goal is just to get y by itself. So I have a product of y plus 1 and I have a product with x minus 2. How can I get rid of the x minus 2s so that I'm left just with y plus 1 without having to distribute? So again, I'm trying to get this term by itself right now. But there's a product with x minus 2. But I don't want to distribute because if I do, I'm going to complicate the problem for me. We need to divide. There you go. We divide by the term x minus 2. Okay. So we divide both sides by x minus 2. Okay. What does that do? Well, then x minus 2 over x minus 2, that divides out. And now I'm just left with the term y plus 1 equal to negative 3 over x minus 2. And I'm just one step away from being able to get y completely by itself. What is that one last step? There we go, right? We could subtract 1, all right? We subtract 1. Right, from both sides. So 1 minus 1, that cancels. We're left with y equal to. Now remember, this minus 1 is a constant, right? It cannot be subtracted from negative 3. It cannot be subtracted from negative 2, right? That minus 1 is like your k value, right? When you think back to rational functions, it's your k value. So I can't subtract it from my a value. I can't subtract it from my h value. So this ends up being another rational function, negative 3 over x minus 2 minus 1. And that right there would be my inverse function. Okay. So notice that they're similar, right? The inverse of a rational function is another rational function, right? That's kind of cool. So this is what we would get. Are there any questions on how we got that so far? What's the last step that we have to do here to show what my inverse function is? Yeah, we want to change y into f to the negative 1 power of x. Okay, so we do one last step here, which is step 4. We want to change y into f inverse of x will be equal to negative 3 all over x minus 2 minus 1. And this right here is my inverse function. Any questions there? So notice how the strategy for getting y by itself or solving for y is different depending on the function that you have. With linear is a little more straightforward. With rational functions, you have to use a cross product at some point. This is the notation. Yeah, we have to change y back into f inverse of x because we need to show, or actually it's not even f inverse, sorry. It's g inverse, right? Because we started with g of x. So the inverse should be g inverse of x. Sorry about that. Okay, but that notation indicates this is the inverse function of your original function. All right. Any other questions before we move on? All right, cool. Next one then. Square root function. All right, let's take a look at the square root function. Any ideas on what this inverse function will look like? If you think of a square root, right? Think of the graph. Think of what it looks like. What do you think the inverse of it would be? Or in other terms, maybe what is the inverse of a square root in general? Yeah, right. It's maybe a power of 2, potentially, maybe. Right, we'll see. All right, so let's take a look. We begin with h of x. That's our function. We want to find the inverse. So step 1 here is to change h of x into y, right? So we have y is equal to 2 times the square root of x minus 3 plus 7. All right. Step 2 says swap x and y. So we get x is equal to 2 times the root of y minus 3 plus 7. All right. Then we get to step 3, where we need to solve for y. We need to get y by itself. How do we begin that process? Where should we start? Yeah, we start with the constant. Notice how most of the time you begin by moving the constant, right? So we subtract 7 from both sides. We end up with x minus 7 is equal to 2 times the root y minus 3. Okay, you're working your way to try to get the y out of that square root, right? What do you think you could do next to get one step closer to having y by itself on the right side? I don't want to square yet because I have a coefficient in front of my square root. Yeah, so I want to get rid of that coefficient first. So let's first divide by 2. All right, which means we divide all of the other side by 2. Okay, so I'm going to wrap this in parentheses just to keep it as one term, but that one term is divided by 2. So we end up with x minus 7 all over 2 is equal to, well, 2 over 2 divides out, and we're left with the root of y minus 3. Now what can I do to get rid of that square root? Now that the square root is by itself, now we can square it, right? We can square it, and if we square one side, we square the other side as well. Okay, so I'm going to take the work up here. That leaves me with x minus 7 over 2 squared equal to y minus 3. Okay, what's the last step now to get y by itself? Yeah, we'll just add 3 to both sides. So we end up with y equal to x minus 7 over 2 squared plus 3. So it looks a little funky, right? But what kind of function is it when you have a power of 2? What do we call a function whose leading power or largest power is a power of 2? Yeah, it's quadratic, right? So That kind of makes sense, right? You have a square root function, so the inverse of that should be a quadratic function, right? Because a square and a square root are inverses of each other, right? So there's a bit of a relationship there where inverses and inverse functions, right, they stay attached to each other. Okay, so then finally, what do we want to do with y? We need to change it, rewrite it into something else. Remember that we started with h of x as our first function. So what should the inverse function be called? There you go, right? So this ends up being h inverse of x. So h to the negative 1 power of x is equal to x minus 7 over 2 squared plus 3. Right? No need to expand this expression, the x minus 7 over 2 squared. Just go ahead and leave it. So this was our step number 4. Right? Change y into h inverse. Any questions so far? Yes. Every square root has an inverse function that is a quadratic. Okay. Now the last one has a disclaimer. Okay. Now we're starting with a quadratic function. And we're going to technically find the algebraic inverse of it. However, quadratics do not have inverses. Why do you think that is? And it's interesting because square roots have inverses, but quadratics don't. So this one is a disclaimer in the sense that if you were to take if you do the algebraic steps on a quadratic, you will eventually arrive to an inverse function. Okay, but a quadratic by definition cannot have an inverse function. Okay, this is something you'll learn a little bit more about, but in order to have a inverse, you need to be a one-to-one function, which means you also need to pass something called the horizontal line test. Okay, we've done a bunch of vertical line tests, right? That one tells you if it's a function or not. Quadratic is a function, passes vertical line test. Sorry, but it does not pass horizontal line test. Okay, because if you draw a horizontal line through a quadratic, what happens? You hit the quadratic twice on the horizontal line. So all of these other functions, if you think about them, square root passes horizontal line test. You can kind of envision that. Rational function passes horizontal line test. Linear function, it's a line, right? Passes horizontal line test. So quadratic is one of these unique ones where if you start doing the steps, you'll get something, right? It'll look like, hey, this is a legit inverse, but it's not really truly the inverse of the quadratic because a quadratic does not have an inverse function, okay? But the reason why I'm showing it to you is just so that you practice the process, okay? Practicing the process, but knowing that this inverse that I get is not truly the inverse of this quadratic, okay? Because it fails the definition of what it needs in order to be an inverse. You need to pass the horizontal line test, okay? So if I think about what this quadratic looks like, it starts up here at +2, and then it's like narrow going down this way. So if I draw a horizontal line through it, it fails, right? So in order to have an inverse, you need to pass the horizontal line test, okay? In another world, we would spend more time talking about all this. You'll definitely see it again when you get to pre-calculus, but I just wanted to give you a preview as to why we're doing it, but why also it does not really truly have an inverse. Okay. And it has to do with horizontal line tests. Okay. All right. So that's just like your bonus knowledge for the day. All right, but let's apply the steps, right? Let's apply the steps so we can see what this would look like, right? Let's see what this would look like. So we begin with step 1, which is to change the g of x notation into y. Y is equal to negative 2x squared plus 2. Step 2, we swap. X will equal negative 2y squared plus 2. Now our job is to solve for y. I want to get y by itself. What can I do? Where do I begin? Yeah, we subtract 2, right? We begin there. That leaves us with the term x minus 2 is equal to negative 2y squared. Okay. All right. I'm still working, trying to get y by itself. What can we do next? Yeah, we want to divide by negative 2, right? Get rid of this coefficient of negative 2 so we can divide by negative 2. Again, this whole term is connected, so we divide the entire expression by negative 2. Okay, so what are we left with? We're left with y squared is equal to x minus 2 all over negative 2. All right, what do I apply now if I wanted to get rid of the square? What operation will undo a square? Yeah, square root, right? It's a square root. So we apply the square root on both sides. Okay. Now here's a reminder. When you have a power of 2, that also indicates number of solutions you need to have. So I hope that this reminds you that when you do apply a square root, there's something that needs to be added to the front of the square root. There's a symbol, a special symbol that indicates you will have 2 possible solutions. Okay, because we know square root and square eventually they're inverse operations, right? So they undo each other. So y comes down. I also have the square root of x minus 2 all over negative 2, but shout out to Ariadna. She gave us, hey, you also need a plus or minus, right? It's like if you were solving any quadratic, right? You're looking for 2 possible roots or 2 possible x-intercepts. So this is where we get that from, where we apply a plus or a minus. Okay. So then finally, right, I don't really want to worry too much about cleaning up the inside of that square root. That's fine. But I do need to change that y back into the inverse notation. Right? So for step 4, since we began with g of x, then I want to change y back into what notation? This would be the g inverse of x. Okay, so this would be our final, right? So it looks good, right? It looks like, oh yeah, like it does have an inverse, okay? Remember, inverse function. Now, if I were to graph this, right, I'd have to graph both parts, right? I have the plus and I have the minus. If I were to graph both parts, watch what happens. Okay, let me show you. Right? The inverse of the quadratic should give us a function, right? A function by definition, which means that this should pass vertical line test. But this is why quadratics never have an inverse to begin with, because the inverse that they do give us are not functions. Check this out. I would have to graph both the positive or the plus square root and the minus square root, right? There's two functions built in there. So if I have the square root, let me look for it. RSQRT of x minus 2. This is divided by a negative 2, right? That's all good. That's my first, right? That's my square root that kind of exists over the x-axis, right? But then I also have to graph the negative one of that. Check it out. This is the inverse of the quadratic function. Right? It's two parts, but you got to think of them as one piece. Now, is that a function? Yeah, it's not a function. Right? The quadratic gives you an inverse, but it's not an inverse function. Does that make sense? So that's why quadratics, because they failed the horizontal line test, do not have inverse functions, because the inverse is a relation. It's not a function. Do you follow? Right? Like they're using the literal definition of a function. Like the quadratic might be a function, but it does not give you an inverse function, because the inverse of a quadratic turns it into like a square root on its side, right? You see both parts. So it's like a quadratic got turned on its side. If you cut it in half, you have the square root part. This is why those quadratics do not have inverses. But mathematically, like algebraically, it looks like they do, right? You go through the steps and you're like, well, I got something. But then if you analyze it graphically, you can see like, hey, this doesn't pass the vertical line test. This fails the vertical line test. So this inverse that we got couldn't be a function. All right. Does that kind of follow? Does that make a little more sense now? Why that quadratic doesn't truly have an inverse? And then all of the other functions did. Linear did. What was the other one? Square root did. And then the rational function did. Right? Those other functions gave us true inverse functions. Okay.